our recent work on neural key phrase generation with syntactic guidance. So this is a joint work with our former intern Wasi, who's a student from UCLA, and also it's in collaboration with my colleague Suming. So I will first start with what's key phrase generation and why we want to tackle such a problem within Yahoo. And then I will present in detail our proposed solution, as well as the experiment results that we have obtained. So what's key phrase generation? So by this task, we're basically saying that given a document, we want to generate a list of key phrases that can summarize the key concepts that have been discussed in the document. So as we are all familiar with scientific document, so if we are given a research paper, basically we're referring to this keyword section where there's a number of keywords about the main topic of the paper. So we want to leverage the title, the abstract, or eventually the full content of the paper and to say, oh, what will be the most important keywords that can summarize this article. So not only scientific papers, a document could also be a web page. So given a web page that we're viewing, we also want to generate a number of key phrases that are mostly relevant to the content of this web page. So if we're reading a page like this, we would find that the keywords like coronavirus vaccine, vaccine cost, vaccine price would be relevant key phrases to this page. Then you may wonder that why such a problem is important. So there's actually a number of real-world application scenarios making this task very important. So one application would be scientific document retrieval, such as for systems such like Google Scholar. You type a number of keywords, then the relevant papers will get returned. So if we have additional keywords that are extracted from the articles themselves, it will help with the retrieval system. Then you might say that, okay, there's already author provided keywords, why they are still helpful? Actually, this is because author provided keywords, they might be inconsistent in terms of the meaning across different domains, which makes the retrieval sometimes difficult. And also there's a recent paper that studies if we use this automatically generated key phrase to retrieve scientific document. They said that even using them in addition to the keywords provided by the authors, it can still significantly boost the retrieval performance. So that's where one application where such key phrase generation can be very useful. And then within Yahoo, we are more interested in the advertising scenario. So we are considering this case called contextual advertising. So basically, if we are looking at a page like on the right about coronavirus, we could eventually show any type of ads on this page. But we find in practice that if we could show an ad that's more related to the content, it will drive more better click and conversion from the user and derive better satisfaction for the advertisers. So in this case, since the page is coronavirus, we would prefer to deliver something related to mask rather than a car. So that we have been proven in practice is working better. So we are also interested in getting relevant keywords from a document in this application scenario. So let's define the problem properly. So given a document, which could be a scientific document or a web page, the goal of this work is to use a machine learning model to come up with a list of key phrases that can summarize the most important concept discussed in the document. Here we have a notion to distinguish these keywords. So we can call a keyword to be present key phrase or an absent key phrase. So when we say a key phrase is present, it means that it appears exactly as it is in the document itself. Or it doesn't appear in the document, but is closely related to the content. Then we call it an absent key phrase. So in the following, we are going to talk about how we can actually deal with these two types of key phrases. So there have been a number of approaches to study the key phrase generation problem. The most typical one, we call it as an extractive approach. So basically, some kind of extraction algorithm will be run on top of the input document to identify a number of text spans, such as name entities or noun phrases. And these will serve as a candidate for key phrase. And then there will be a ranking model to measure the relevance between each key phrase and the document and to decide the final set of the relevant key phrase. So usually this approach works pretty well, but it also has some drawbacks. So first is that this kind of approach, they cannot generate the so-called absent key phrase. So if we look at this table that shows a number of benchmark data sets across the scientific domain or the web domain, and we can see here, for all of them, there's a large percentage of key phrase that actually doesn't appear in the document. So it varies from 26% for scientific domain to up to 62% for a web domain. So that means if we ignore this absent key phrase, we may not have a comprehensive set for keywords that can describe the page content. And also for this extractive approach, it cannot work on its own. It heavily depends on the ranking model and the feature engineering related to the ranking model to be able to come up with a high quality key phrases. So this motivates people to think about a generative approach, especially given the popularity of these neural language models. So they were thinking that if we can actually generate the key phrase by simulating the human thinking. So if we are given a document, how would we assign the keywords to the document? So basically we're going to read the text and understand what's the content and what's the context information around the page. And then we will be able to summarize the most important key phrase. So motivated by this, in 2017, people proposed the very first sequence-to-sequence model for this key phrase generation task. So this model is very famous. It's called copy-RNN. Basically, it uses a RNN-based encoder and a decoder to model the input documents and generate the ground truth key phrase. So this approach, the decoder generates the key phrase one by one using beam search. And we call this schema as one-to-one. So if you have any question, please feel free to interrupt me because I assume that you are all familiar with RNN and all these beam search related techniques.
Yeah, Xiao, if I may just interrupt. What we typically do is, like, if there are natural breaks in your talk, like every 15 or 20 minutes, on your side, just pause and ask if there are questions, and that's helpful in this online setting.
Sure.
Okay, thank you.
Yeah, so
I did have a question regarding previous slide and present versus absentee keywords.
Mm-hmm.
I guess I'm not entirely clear on what the task is and why ranking them doesn't give us the absentee. Like, couldn't you just have a threshold value for the ranking?
The ranking works, and it's usually with the extractive approach, people usually use a ranking approach. You first come up with a number of noun phrases from the input document, and then the ranking model will compute a relevance score and then set a threshold saying that everything above would be my candidate key phrase.
And so, yeah, in that implementation, it sounds like you would be able to measure absent key phrases.
You will be able to measure absent key phrase, but the approach itself doesn't allow to generate absent key phrase. Because usually this approach is just doing tagging on the input text, saying that, okay, which part of the document or which words will be a constituent of noun phrases or
oh, I see.
entity. So it's just by tagging, but it will not come up with new words that doesn't exist in the input document.
I see. Okay, thank you.
So to clarify, by an absent key phrase, you mean a key phrase which is related to the document, but does not at all occur in the document?
Yeah,
is that okay?
The entire text span, because for example, if an absent key phrase has two words, so basically it means the two words doesn't appear together in the text. If they appear far apart in the text, it's still considered as absent.
So,
Gotcha.
can you think it as like a paraphrase or something like that?
Yeah, you can consider it as a paraphrase of a present key phrase. Yeah.
Okay.
Thank you.
Yeah, so with this copy RNN network, as we said, they're using RNN as decoder and encoder for generate key phrase. And then they also introduced a new mechanism called copy mechanism that relies on attention to deal with out of vocabulary words. So if they say a word in the input document, it's kind of rare, not appear in the vocabulary, but through attention, they know it's an important word. So they still generate it as part of the key phrase. So that kind of improve the quality. And then there's a number of follow-up work to improve this copy RNN idea. And then there's one particular work that I want to mention here is called cat sequence. So this model uses exactly the same architecture as copy RNN, but one major difference is the way that they generate the key phrase. So in a copy RNN case, the key phrase for a single document, they are generated one by one using beam search. But in the cat case, they actually consider all the key phrases as a concatenated sequence. So they try to generate all the keywords at once. And there's a number of reasons for doing this. The first is to increase the diversity of the generated key phrase, because when using an RNN-based model, you usually generate a keyword based on the words that have been generated already. But if you generate the key phrase one by one, then it means you only consider the current key phrase. But with this cat sequence schema, you are actually also considering the keywords, the key phrases that have been generated before. So that will allow the model to generate more diversified key phrase. And also another reason for using this schema is with copy RNN, usually people say, okay, we want to generate the top K key phrase. And it's usually hard to determine the value of K, and that may vary across different documents. And with this cat sequence, it will take into consideration the length of the input document. So you don't need to manually assign a K value, and it will vary according to the input document. And in our work, we actually will follow the 1-2 sequence schema for generating the key phrase. So overall, I think the literature has shown that this generative approach has a better performance than this extractive approach, but they still have some problems that haven't been addressed yet. So one problem we see is that all these problems, approaches, they are not designed to process very long document. So in the scientific document setting, they are only considered the abstract and the title as input document, which is usually around 200 words. And in the web domain, if we look at the data for the KP times and in-house data here, the average length is close to 1,000 words. So that makes this very long and very efficient to be processed by an RNN-based model. And another approach of this a problem with this generative approach is that they are not very good at generating present key phrase. So from this copy RNN work, they actually show that if they don't use this so-called copy mechanism, the F1 score on the same data set could drop from 0.278 to 0.08. So that's a very significant difference. And using copy, they will be helpful to generate the present key phrase. But we discovered there's another problem associated with this, is that the meaning of the word could change with a copy. So for example, in the input text, maybe we have something like flu shot. But at the generation time, with attention, there will be no guarantee that the generation model will consider these two words together as a key phrase. They might think, okay, the word shot is rare and it's more likely to be an important word, and just copy the word shot. And then that will completely change the meaning and the downstream retrieval task. So this is also one problem that we want to address in our work. So is anything good so far? Okay, I assume silence means good. So now I'll move to our approach. So basically we design a new neural key phrase generation model, and we want to use this model to address these two problems that we have seen with the existing generative approach. So the first is to how we can deal with long document. So we propose, instead of using the full document as an input, what we could do is to select the top K most important sentences and only use these sentences to generate the key phrase. So for that, we propose a so-called sentence selector to do the job. And once we have this important sentence being selected, instead of relying on a single extractive model or generative model, we have proposed to separate these two tasks to extract a present key phrase or generate absent key phrase from the input text. And we hope that with this separation, we would be able to achieve the best from both words. So for salient sentence selection, we first need to define what a salient sentence. So here we are adapting a very basic definition. So we say a sentence is a salient sentence if it contains a ground truth present key phrase. So this is very straightforward. And then for the absent key phrase, actually there are many possible ways of defining the salient sentence for absent key phrase, but we are simply considering the case if a sentence that overlaps with an absent key phrase. And then the salient sentence selection task is actually a binary classification task where we want to predict a binary label for each sentence in the input. So the positive label will indicate that a sentence is a salient sentence.
What does that mean when a potential salient sentence contains an overlap with an absent keyword?
Yeah, this is basically means that given when we at the time we train our model, we need to know what are the salient sentences. Yeah. And none of this data come up with a definition of a salient sentence. So we actually define, okay, we are going to scan each sentence. If that sentence overlaps with our absent key phrase, we will consider it as a ground truth, or basically the positive label that we want to predict.
Yeah, that makes sense. I'm just not clear on what you mean by overlap with absent key phrase.
So let's say if you have a absent key phrase, which is called coronavirus shot, and then you find that there's a sentence talking about coronavirus vaccine. And then this sentence and this key phrase overlap on the word coronavirus. And then you would consider that this sentence as an important salient sentence for this absent key phrase.
Okay, so it's like a degree removed through the words. Like one sentence has the keyword, and then we saw another sentence without it, but it has other words that are the same. Am I understanding?
No, I mean, if in the input sentence, it have a number of words, as long as there's one word that overlap with it's the same as a word in the absent key phrase, then we consider it as a salient sentence.
Okay.
Yeah, this is because there's no standard way of defining a salient sentences. So we just come up with this very basic definition. Yeah, and then there also will be a number of improvements that could be added to make a better definition for this salient sentence detection.
So does that mean that you're looking for similar words as like because you mentioned vaccine and shot and how vaccine is similar to shot. So does that mean like when you're looking for salient sentences, you're also considering like synonyms for finding these absent words?
No, actually, for selecting the salient sentence, we're not yet looking at the similarity between the words. We are just saying that if the same word has appeared, so in this case, we only look at the word coronavirus, that's exactly the same as it appeared in some sentences.
Oh, so in this case, you're only considering coronavirus then.
Yeah, a better approach would be actually consider the semantic similarity between a word and the one sentence or eventually a bag of sentences. That will be a better approach we are trying to do in our future work, but for this particular work, we're only considering this very basic definition.
Okay, cool, thank you.
So how did you define the absent key phrase?
So absent key phrase basically means that a key phrase doesn't appear in the document.
But maybe the question is, where do you get those absent key phrases from? Are they annotated somewhere?
Yeah, they are. So for the scientific document we have, these keywords are also provided, like the keyword section for document. And for the web domain, we have two data sets. One is public data sets from news domain. All those pages are public news articles. And those keywords are provided by professional editors. And then we also have our in-house data sets, that's general purpose web page. And for those, we are coming up with the key phrase from the search click log. So that I basically will present later. So if we have a search log, if a query frequently leads to a click on a page, then we would consider that this query is closely related to the page, and it could serve as an absent key phrase for that page.
Mm-hmm.
Yeah, okay, so if there are no more questions, now I'll continue. So for this sentence selector, we are adopting this transformer-based architecture. So for each input document, we can consider it as a sequence of words. And each word, we use an embedding layer to convert from a word to a fixed length embedding. And then this embedding will be fed into a transformer-based encoder. And this encoder will produce embedding for each of these words. Then we will do a max pooling and a min pooling at a sentence level. So if the sentence contains 20 words, we will do a max pooling and a min pooling over these 20 words. And then we will concatenate the pooling results. And this will give us a representation of the entire sentence. And then we will feed this sentence into our classifier. So our classifier is basically a feed-forward network with a max-out activation function, and it will predict in the end a binary label if this sentence will be salient. So any question here?
So would you be giving it all sentences at once or one sentence at a time and giving out?
So it's all sentence at a time.
Okay, and then so is that one binary label for each sentence?
Yes.
Okay.
Yeah, so basically here we're adopting this transformer-based architecture. I assume that you're all familiar with transformer. So it's basically attention-based model. There's no sequence. It just uses this multi-head attention to use a word to attend all the other words in the document to learn the context. And then this attention layer is usually followed by a feed-forward network to come up with this representation, hidden representation. And this has been the new state of the art for many natural language processing tasks. And since it's using attention, so by nature, it breaks the dependency on the surrounding or preceding text. So it can be processed much faster and processing a long document by default. So as we said, the input word will be first converted into an embedding using the embedding layer. So here we are actually consider 5 components for building an embedding for a given word. So the default one will be the word representation. And then we're also using a one-dimensional CNN network to build a character level embedding for each word. And also we have a part of speech tag embedding. And also we have an absolute position embedding is basically which position a word appears in the input document. And also we have the 5th embedding, which is a segment embedding that indicates which a sentence a word would belong to. You can consider this as a relative position for a word. And for each of these embedding, they have the same length. So we did an element-wise addition to form a word embedding. And this will be fed into our transformer-based encoder. And as a learning objective, as we are doing a binary classification, so we using this weighted cross entropy loss. So the only difference with the default cross entropy is that we are adding a weight to balance the positive and the negative samples here. And this is a learnable, this is a hyperparameter that we will set.
Xiao, I have a question on the previous slide.
Sure.
Yeah, if you're using a pre-trained transformer, it only operates on text, right? So are you, so how are you encoding, like for non-textual data, like the part of speech tag, for example? Or
So first, we are actually not using a pre-trained
okay.
transformer. We are just building it from scratch.
Oh, I see. Okay. Okay. Okay.
Yeah, so once we have the sentence, important salient sentence detected, I'll show you how this extractor and generator will work. So as we said, the present key phrase extraction and absent key phrase generation are two separate tasks in our setting. So for present key phrase extraction, basically given the list of salient sentences, the goal is to predict a binary label for each word in the input sentence. And the positive label will indicate that a word is a constitute of a present key phrase. So what does it mean? We can see from this example. If we have 3 sentences selected from input document, they are separated by this special token end of sentence. And then the extractor will give each of the word appearing in the input document 01 label. And then once this label are generated, we'll scan through it and we see, okay, there are 2 ones, they are next to each other. And then we will look up the input text and to see, oh, this corresponds to word coronavirus vaccine. And then this will become one of the present key phrase. And then we'll keep doing the same throughout the text. If there's another keyword words that labeled as 1, then it will also be converted to another present key phrase. That's how this present key phrase extraction works. And then for the absent key phrase generation, so basically it will be given for the same input salient sentences, and then the key phrase will be generated in a sequence to sequence fashion. So here, again, the same input has been provided, and the generator, as we said, it will generate all the key phrases at once as a concatenated sequence separated by some separator. And then we will split them into separate key phrases in the end. So maybe here with this example, it will be easier to see what actually we mean by absent key phrase. So you will see that this absent key phrase here, vaccine cost, it doesn't appear directly in the text, but we can see it's closely correlated with these 2 words marked in red. And previously with the present key phrase, this word appears exactly in the input text. So is there any question?
Yeah, Xiao, just to clarify on the previous slide, if you have just if you had just one word, right? Like does the generator handle cases where like suppose the word coronavirus appeared, or suppose, actually I take that back. Suppose the word COVID appeared in the original text and you just wanted to generate the word coronavirus, right? So there's actually 0 overlap between the absent phrase and the text. Like, is that case handled, or where would generate a synonym?
So I think it depends on the word. If the word is some words that appeared in the vocabulary, I think it's possible that a synonym would be generated. But if it's a brand new word, then it's unlikely to be generated, and then it will only appear in the target keywords by the copy mechanism.
Okay.
So I think it depends on what the word is. If it's a common word, or it's something already appear in the dictionary, and then it's likely to be generated. It can generate the synonyms.
Okay, so for common words, they can be generated even if they don't appear, even if there's 0 overlap with the
Yes.
with the original text. Okay.
Yes.
In those cases where there's zero overlap, would they fail to be identified as a salient sentence?
They would.
Okay.
Okay.
Yeah, that's actually the drawback of the way that we're defining the salient sentences. Actually, we'll show the result, and you will see that actually this salient sentence selection in our setting is mostly helpful for the present key phrase generation, but not much for the absent key phrase generation. I think
That makes
it's
sense.
because that we are not defining it in the best way, I would say. So this is the architecture of our extractor and generator part. So again, the salient sentences as input, they will be presented as a list of the words, and each words will be represented through this same embedding layer. And then these will go through, again, a transformer-based encoder, and we obtain a representation for each word. And then each word will go through this multi-layer perceptron, a feed-forward network, to get a binary label to say if it's part of a present key phrase. And from here, we will be able to identify the present key phrases. And then we also have the generator to generate the absent key phrase. So they will share the same encoder for the input text. And then the decoder is also transformer-based. It will take the encoded input and also the output that have been generated so far, and then to predict the next word over the vocabulary using a softmax function. So with this decoder, it will produce a distribution for the words to decide which will be the next. And then in our approach, we're also adopting this copy mechanism to deal with this out of vocabulary words. But as we said, we don't want a word to be simply copied because it's part of the text. We'll try to not change the meaning by copy a word if it's already part of a present key phrase. So we introduce a modified version of copy called informed copy. So basically what it does is the regular copy will come up with a distribution of the input words based on the attention given a word, its attention with all the input words. And then we will check the present key phrase that have been already generated. And from here, we'll say, okay, if a word has been generated, then we will block its distribution. And when we sum up it for the final distribution of an absent word, and then this word will not appear and will not be a candidate for generation. And this way, we'll only make sure that the absent key phrase generation will generate some new words, but not overlap with the present key phrase. And in a way, it also helps with diversity. So is this part clear?
Sorry, I have a question. So, I mean, in order to define what a salient sentence is, you need to have a bunch of absent key phrases at first, right?
Yes.
So why did you need to generate the absent key phrase again?
Well, when we identify what will be the salient sentence, we are using the ground truth absent key phrases. And that's what we use for the training purpose. We use the ground truth key phrase to detect what will be the ground truth salient sentences. And then we will train the model to generate the same absent key phrase. We will generate the ground truth key phrase, try to generate the ground truth key phrase, and then use the loss function to adjust the model and make it generate the words that are closer to the ground truth.
In your test data set, do you have these absent key phrases? Are
Yes,
you
we
using
have.
the same absent key phrase?
Yes.
Okay.
Okay, so as we said, the extractor is simply a binary classifier. It will predict the probability of each word being a part of a present key phrase. So here in this formula, it's basically the probability given the output of the last hidden layer of the transformer, the probability of a word being a present word, part of a present word. And then this is the embedding from the transformer decoder. And here it goes through 2 layers of feed-forward network. And this is a sigmoid function to compute the probability. And then as a decoder, it basically predicts the probability of generating a word given the previously generated word and the current hidden state. So it will compute a softmax over the last layer of the transformer layer. And then here we have this informed copy mechanism. So the overall idea is to only let the decoder to copy the word if the word is not already part of a present key phrase. So here, this formula, it basically presents the probability of generating a word. And it has 2 components. In a traditional generative model, it will only have the first part, which is a probability of generating this word, not using copy. Here, UT equals to 0 means not using copy, and equals 1 means using copy. So in a regular generative model, there will be only the first term. And then in our case, we're using the copy mechanism, then there will be 2 terms. The second term will be the probability of using copy multiplied the probability of generating words when copy is used. So for the probability of generating a word given copy is basically its attention weight that's computed between the output of the decoder layer. No, sorry. This is output of the encoding layer for each of the word appearing in the input text, and this is the output of the decoder layer of the current word. So this computes the attention weight, and that's a probability here. And then for the probability of using or not using copy is basically a sigmoid function based on the output of the transformer layer as well as a context vector. It's a concatenation of these 2, and the context vector is basically, if we see from here, it's a weighted average of all the output from the encoding layer for all the words in the input. And this together will give the copy mechanism. So in our case, we simply say that if a word is already part of the present key phrase, then we will set this part to be 1 and this part to be 0. So it will only be copied, only be generated by the generation model, but not copied from the input text. Any question here? Okay, so now let's look at the loss function. So for the generator and extractor, the loss will be a weighted loss, weighted average between the extractor loss. Sorry, it's extractor generator. So extractor loss and the generation loss. And for the extraction loss, it's again a weighted cross entropy between the negative and the positive labels. So the negative is not a part of a present, and positive is part of a present key phrase. And then for the generation loss, here we are introducing the keyword generation loss, which is the negative likelihood of the ground truth keyword. So it's given the previously generated keywords and the current word, sorry. The probability of generating the current word. So it's a negative likelihood. But here, if you pay attention to the notation, here we call it a loss of W. It's a loss of generating the keyword. It's not the full generation loss, as there's some second parts that I will present here. So in our work, we are introducing the so-called syntactic guidance. So instead of using the words itself, we are saying that since most of the key phrases, they are noun phrases composed of either nouns or adjectives. So it would be helpful if we can know the part of speech tag of each word, so that we will avoid generating the pronouns or other irrelevant words and try to focus on nouns and adjectives. So to this purpose, we are introducing a multitask learning to predict the part of speech tag for each word. So here again, this part multitask learning, it shares the same architecture as the generation task. Just here, we are using a lower layer output of the decoder to predict the distribution over a part of speech tag vocabulary. So the only difference with the absent key phrase generation is that we are not using the last layer of the decoder, but using a middle layer, because that turns out to have better performance than the last layer. And then the overall generation loss will be the loss from the keyword generation part plus the multitask learning part for the part of speech tagging part. And these together form the generation loss. And then that will be again combined with the extractor loss to form the final loss function for this extractor generator model. So is anything clear? Any questions? Okay, if not, we are going to move to the experiments.
Xiao, a quick question on the previous slide. Sorry, I missed this. Once you have the part of speech tags, what do you do with it again?
No, we are trying to predict the part of speech tag for each word, for each key phrase.
Okay, but once you've predicted that part of speech tag, how is that part of speech tag used?
It's not used. We're not using that, but
Okay.
we are just saying that trying to teach the model to learn part of speech tagging as part of the embedding. And we expect that would help with the key phrase generation task,
okay.
So that it will more generate the noun and adjectives and avoid other types of tags.
Oh, I see, okay.
So itself, the tag itself is not used. It's just we use this to provide kind of syntactic guidance to the keyword generation task.
Okay, but wouldn't it be sufficient just to provide it as input, like, or like, what is the benefit of also producing it? I guess maybe.
Because we want the model to learn how to generate, to learn the difference among the. So as input, we actually, as you said, we provide part of speech tag as part of the embeddings, but that's for the input text. And we also want to teach the model to learn the tag for the generated key phrase. For each word in the generated key phrase, what would be the corresponding tags?
Okay.
So for the experiments, we are considering datasets from two domains. One is a scientific domain, the other is a web domain. For scientific domain, we're just taking 5 benchmark datasets. They're listed here. And these are scientific articles. So the input will be the title and abstract of each article. And then there's a list of key phrases provided by the authors of the articles. And then the model is trained with this KP20K dataset because it has a larger amount of data, and all the others, they are tiny datasets just used for evaluation purpose. And this is a very standard setting in all these key phrase generation tasks. And then we also consider a dataset from the web domain. The first dataset is KP Times. It's also a public dataset that's composed of a number of news articles. And these keywords are ground truth keywords are provided by professional editors. And then within Yahoo, we are working on advertising using this, trying to use this technique to generate the key phrase. So we are randomly sampling some web pages and use the title and the body of those pages to serve as the input document. And the way that we generate the key phrase is that we are using the search log from Yahoo Search. So we look at the queries that are often leads to click to a given page, and we assume that that basically means the query itself is very relevant to the page content. So we consider these queries as the ground truth key phrase, and this query itself, it could be present and also be absent. And here is how these two data sets look like. We have seen this table a couple of times. So these 5 first ones, they are from the scientific domain, and the last 2 are from web domain. So for KP20K and also this web domain data set, we have roughly 20K of training samples. And the others, they have very tiny data set. And then we can see that the average length for the scientific domain is usually less than 200 words on average. And for web domain, the document is much longer. The average is close to 1,000 words. And then we have this column that shows the number of salient sentences being detected in the document. We can see that in either case, the percentage of salient sentences is pretty low. It's 30–40%. So that basically means that we never need to use the entire document to generate the most representative keywords. And if we look at the number of ground truth key phrase, so most of them, I would say it's around 5, and there are 2 scientific data sets, they have around 10 keywords on average. So as baseline, here, as we said, we are going to consider this 1 to 6 schema for generation, and there's a number of baselines follow the same work, and they are introducing different mechanisms to improve the diversity and also the coverage of the topics within a content. And we, in addition to this state-of-art approach, we are also considering a variant of this original cat sequence approach, because we are using a transformer-based architecture. So we replace the RNN from the original cat sequence work and use a transformer to do the generation. So that's our baselines. And as metric for sentence selection, we're considering precision and recall to measure the performance. And then for key phrase generation, we're using F1 at M and F1 at 5. This is also the standard metrics using in the literature. And here 5 means retrieving 5 keywords for each document. And if there are not 5 words being generated, then we'll assume that they are just the random words. So they will be contributing to lowering the precision without changing the recall. And then this F1 at M basically means the number of keywords being generated by the model. So it could be any number depending the actual input document. And yeah, so any question here? Okay, so here's a few implementation details. Basically, we are using a fixed vocabulary of the most frequent words, and all the embedding we're considering have 512 dimension. And as a transformer for both the encoder and decoder, we are using 6 layers with 8 heads. And for the key value dimension, it's 64, and the feed-forward network fully connect layer has 2048 as dimension. And during the training time, we actually gave 70% of the weight to the key phrase generation task and 30% to the part of speech tagging task. And then between the extraction and generation task, we are giving them equal weight. And then we are using Adam optimizer. So at test time, when we are generating the key phrases, we are using a greedy search approach. We are not considering beam search here because as we are concatenating all the key phrases together, greedy search seems to be more efficient. And also we are trying to avoid generating the repeated trigrams. So if the word already part of a trigram, or generating a word will lead to a trigram that has been already generated, then we will also avoid generating that word. So this actually we find it also helpful for improve the performance. And here is a F1 score on the scientific data. So each column here presents one data set. And on the top section, it's the performance on the present key phrase generation. And the lower part is the absent key phrase generation. So we can see that with the default cat sequence baseline, we are improving the F1 score from 0367 to 0381. And according to our statistic significance test, this improvement is actually significant. And this is the same across all these different data sets. And then for the absent key phrase generation, we are observing similar improvement. So for all this data set, we are improving the F1 score for M and at 5, except for this one, but this one is a very small test data set. Say that majority of the case, we're still improving. And then here's the F1 score on the web domain data set. So again, for both these KP times and our in-house data sets, we are improving over the baseline for the present key phrase generation significantly. And the same happens for the absent key phrase generation.
I have a question.
Sure.
Are any of these models using so the absent key phrase generation is low? Like it seems low to me. Are any of these using like a semantic comparison rather than just like an overlap method?
No, actually, yeah, you actually raised a very good question. These F1 scores looks extremely low. It's because absent key phrase is kind of very hard to generate the exact word as what's in the ground truth. So here we are only considering F1 score because in our application scenario, we actually don't want to generate many keywords because of precision matters more for us. And then in the literature, actually for all these papers, they consider another metric, which is recall at K, and they consider this K to be very big. They measure recall at 50 or even larger. And then without looking at precision, the recall for absent key phrase can reach a relatively larger number. So that's how people evaluate the absent key phrase. So they use F1 score, and they also use recall at a very large K. Because by considering a small number, it's very hard to come up with exactly the same words as a ground truth.
Mm-hmm.
Yeah, but I haven't seen any work that use the semantic similarity to measure.
Okay. When you say recall at K being the number of keywords generated?
Yes.
Oh.
Yes,
Okay.
so they can say that, okay, especially for this one-to-one schema, because for 1-to-6 schema, it's a bit difficult because depending on how the model is trained, you cannot predefine the number of keywords that you want to generate for each document. But with this one-to-one schema using Beam search, you can say, okay, I want to generate 50 words for each document. And then you can see among these 50 generated key phrase, how many of them overlap with the ground truth.
And do you select ground truth cases that only have the K number of keywords?
I don't think I get your last question.
So F1 at M, F1 at K, F1 at 5, you're telling your model generate this many keywords, right?
Mm-hmm.
When you evaluate that, what ground truth do you use? Do you select one that has that or do you truncate the ground truth? How do you compare if it's is there ever a size mismatch between?
I see. So for ground truth, we're using everything. And here, when we say 5, meaning that we look at 5 key phrase generated by a model.
Oh.
And
okay,
if it's M, we look at all the key phrase generated by a model.
Okay, so a potentially very poor recall score then.
Yeah.
Okay, that makes sense. Okay.
Yeah, so back to your question, I think you raised a very good point that I'm going to address in our next slide. So here we see that the F1 score for the absent key phrase is very low. And that actually makes us thinking, are we really generating some meaningful key phrase, or is it just by some luck we're doing better than the ground truth? So we did some editorial evaluation for our in-house data sets. So basically we randomly sample some web page and let the model to generate the key phrases using our model. And then we ask professional editors to judge how relevant these keywords are to the original page content. And then they are given a grade of excellent, good, and fair, and bad. bad means they are completely irrelevant. Fair is kind of slightly relevant, I would say. And good and excellent are those ones that we really want for a given page. So here we report the precision at M for our model. And we can actually see it's very interesting for both present key phrase and absent key phrase generation, the precisions are comparable. And even for excellent and good, absent key phrase are slightly higher than for present key phrase. That could be because absent key phrase, they have more flexibility to come up with synonyms and for synonyms that are related to the content but doesn't appear in text. So we didn't do comparison with the baselines, but just looking at the results, we are kind of very happy with the quality of the keywords that are being generated. And then we also did some ablation study to evaluate each of the proposed component. So the first line is our approach with all the components being present. And then here, if we remove the sentence selector, we will see a significant performance drop for present key phrase. And then, but for absent key phrase, the drop is very small. So I think this is, as we discussed, it's related to the way that we're defining the salient sentences. So for absent, it's not the best way of choosing the sentences, so they're not turn out to be very helpful. Well, they are not being helpful in terms of the improving the quality, but in the meantime, we are actually reducing the size of the input, but they are not hurting the performance. So still it's an advantage. And then with this informed copy, it's designed to improve the absent key phrase generation. So we didn't observe anything for present key phrase, but for absent key phrase, we see some difference in the F1 score as expected. And then for multitask learning, here for this particular data set, we are not observing significant difference between using and not using multitask learning. But when we tested it with our web data set, we do see like 1% or more improvement using multitask learning. So we still believe it's a useful technique, but just with this public scientific data, we are not seeing it. And also we evaluate this impact of these different embedding components. The default one is a word embedding. And then when we add character embedding, segment embedding, and the part of speech tagging embedding, each of them improve the precision, the F1 score a little bit. And especially for this part of speech tagging embedding, it improves about 1% of the F1 score. So we consider this also as part of the syndication that syntactic guidance that are provided by these tags. And then when we compare the quality of the sentence selector, here we are considering very naive baseline. And also that's what's most commonly used in the literature. When people are encountered with long documents, they simply truncate the document by taking the first a few words. So in our setting, we are picking the N sentences for up to 200 words. So N is a very number across different documents. So here we are comparing the precision recall between our sentence selector and this baseline truncation-based approach. So if we look at the scientific domain, we will see that for baseline, the recall is very high. So this is actually expected because the average document length is, I think for 3 of them, they are less than 200 words. So that means we don't need to do any selection. The majority of sentences will be there with this default baseline approach. So that's why they have very high recall. And we are having a lower recall compared to them, but higher precision. But if we look at the web domain where the document is much longer, then we will see with our approach and the baseline approach for the same amount of sentence or words being selected, our approach has much higher precision. And we think that this better selection of the most important sentence actually significantly contributes to the improvement that we observe for the downstream present key phrase generation. So finally, I want to quickly discuss how we actually use this key phrase generation for advertising. So we have seen, given a web document, how we can generate the key phrase like these ones from the content of the page, from the title and its body. And then once a user comes to visit this page, there are typically some ad slots appearing on the page, and we need to decide what ads to show here. And with this contextual targeting, we want to show some ads that are related to the page content. So in the backend, what happens is that advertiser, they have an ad, they come to our system and defines, okay, we want to show our ads to the users who's interested in a number of topics. So they define the topics. It could be in the format of a number of keywords, could be something related to mask, coronavirus, flu, and so on. And then in the backend, we will have a semantic matching system that can bring these generated keywords from web page to this advertiser provided keywords. And then through this matching, we will know for a given page what will be the related ads. And then when the user comes in, these ads will be sent for auction. And some of them, they may win the position and being shown to the user. And we have experiments. I'm not going to present here because it's kind of confidential, but I can say that with techniques we proposed here, we actually improve the relevance of the ads being retrieved for a given document. So to conclude about this work, so in our work, we actually propose to use salient sentence selection to deal with long document. And we find it very important and very helpful for long documents such as a web page. And also we are separating this present key phrase extraction and absent key phrase generation task into two subtasks. And we find that by doing this, it helps with the performance and can beat the baseline that purely rely on generative models. And as future directions, so as we have said, our approach is trained from scratch. So we just define the network architecture because our training data is relatively large. We have at least 20K training samples. So we train the model end to end with our training data. But something very interesting would be see if we can use the pre-trained language model for this task, would it further boost the performance because they have a much better understanding of the word by what we can learn from the test. And also, we are adopting a very simple definition for the absent key phrase, and it has a number of drawbacks, so that as for now, we are not seeing much improvement for absent key phrase. We only reduce the computation, but not really boosting the performance. So we are also investigating better ways of defining salient sentences. And hopefully with that, we could boost the keyword quality for the absent key phrase as well. Okay, I think that's pretty much all I have. So if you have more questions, I'd be happy to take them.
Yeah, thank you for your great presentation. So I have two questions. First, can you move back to where the equation of your copy attention is?
Here.
Yeah, here. Yeah, so I'm wondering, so you did, you exponentiate each term for the denominator, but why did you not do it for the numerator?
That's a good question. I think that's probably how it's defined in the original copy mechanism paper. I have
for every copy mechanism paper we are using.
I was referring to the copy RNN paper. So
yeah.
That's the paper, the first time they introduced this copy mechanism.
Yes, we are using we will exponentiate for each term.
Okay, maybe then it's a typo. I need to double check.
Okay. Yeah, second question, like, except the grid decoding and the beam search, did you try any other decoding strategies like the nuclear sampling or top K?
No, we didn't. We just tried the beam search, but the problem is that as now the target sequence is a concatenated sequence of all the keywords, it becomes very long. So we were not able to experiment with a very large beam size. So with a small beam size, it doesn't improve the performance. And also with this cat sequence schema, most of the literature, I think we see they are using greedy search.
Yeah, so I mean, like it's quite counterintuitive. Like I see a lot of generic tasks we are using beam search. So because like great decoding will be time consuming. So yeah, anyway.
Yeah, so for beam search, for this one-to-one schema, it's commonly used.
Yeah, I see.
But when we consider the sequence, all the keywords as a single sequence, the sequence itself becomes very long, and then using a large beam size will be very costly.
Okay, yeah, thanks.
It is, so beam search to me seems like something you would use when tokens have a dependency on each other, or like there's some sort of like natural ordering to them. Maybe it's because I don't understand beam search very well, but why is it being used here?
We are not using beam search. We are using greedy search.
That would make sense. Okay. Because beam search would just keep track of like a certain amount of paths, right? Of token. Okay, so okay. Thank you.
Yeah, hi, Xiao. I have a question. So I've seen some approaches to to keyword extraction and even generation, which are similar, where you can view the problem as a machine translation problem, right? Where your source language is the language of the original documents, and your target language is the keyword. So it's still the same language, but you're kind of translating it. The translation is viewed from a going from like a very long document to a very short set of keywords, right?
Yeah.
Now, if I were to take some like off the shelf, like sequence to sequence model and just run that on your data, do you think that would work for this task, or is there something, or is there something custom about your model that is going to be better than just using something like off the shelf?
I think it would work because actually initially when we started working on this, we were also considering using this neural machine translation model, as you said, taking the input document as the one language and then the key phrase as a target language. So we did that experiment.
Okay.
And I think it also gave very promising results. And also, as I said, the pre-trained language model that we're discussing, we're more thinking about using this kind of a pre-trained machine translation models to do this task.
Yeah.
I think the text, the problem formulation is definitely valid, and we have tried that as well.
Okay. Okay. Yeah. I also think the pre-train may give you a big boost because the pre-trained ones have been they use such enormous amounts of data. The embeddings might be able to better capture synonyms and related words than just training it from scratch. So. Yeah.
So I think how much the pre-trained language model would also depend on how much training data we have. So we have this assumption that if we have only a tiny amount of training data, then pre-trained model would help a lot with the performance. But at some point when we have large enough training data, then maybe it will not be very helpful, but it's something that we are trying to evaluate at the moment. Yeah.
Okay.
Yeah, it's interesting how you took the like raw F1 scores and then sort of made them relevant to your application. It seems like they did pretty well, but are you still, like you mentioned, like the saliency detector was not very good. Are you currently working on that, or are these results good enough for the application?
We're still working on improvement. Yeah, so detecting better salient sentences is the one of the direction that we are pursuing.
Okay. And then can you say a little bit about what properties on what kind of web properties on which this is used? Is it like for Yahoo News, or is it on mobile properties?
It's mostly for web page.
Okay.
So for the web page that want to show an ads from Yahoo system,
okay,
we're actually trying to understand the page content and show the ads accordingly.
Okay. Okay.
So I'm wondering, for the model output the keyword, does it appear in certain order? For example, the salient keywords appear, like comes out first, or, you know, does it have certain pattern of outputting the keywords?
Yeah, this is actually a very good question. So at the beginning, when we start exploring this approach by putting all these keywords together as a single sequence, we're wondering if this order actually matter at all, and what will be the order of the keywords being generated. So we try to change different order to have the keywords as they appear in the documents, or important keyword first, or present key phrase first, or just a random order. But in the end, the output quality turns out to be the same. There's no major difference. Because I think it's a lot depends on the way that the model works, because it's a transformer, they are just using attention to measure the similarity between each word to the rest of the document. There's no this notion of concept, sequence. Does this answer your question?
Yeah, I think that's like an interesting finding. Also, I have another question about trying to figure out the intuition behind the multitext learning part, about trying to predict the part of speech tag, since you already like embedded that information in the input. So why is still like predicting that?
In the input, we are providing this part of speech tag for each of the input tokens. But then when we generate the generator is used for the absent key phrase generation. So there's chances that the generated keywords, they will not be part of the input text. So we hope that by generating the part of speech tag for these new words, and it will help the model to learn the better word to generate.
Oh, so you're predicting the new word, not the...
Yes, so the part of speech tag is not used for the present key phrase extraction part, because for that part it's obvious. Each word is already part of the input text. We know already what's the tag for it.
I see.
So it's multitask learning is only for helping the generation part.
I see, thank you.
Did you do any analysis, since you used attention on like what words were being paid attention to instead of like the keywords that they were going to, like, did you notice like anything in that? Did you do anything like that?
Excuse me, can you repeat your question? I didn't hear you very well.
Oh, sorry. Did you do any analysis for seeing like what was it that your transformer decoder model was paying attention to? Or like what key phrases they were looking at instead of the ones that they were supposed to?
No, we didn't have that level of details.
Okay, got it. Thank you.
Any further questions for the speaker? We still have a few minutes left. Okay. Going once? Going twice? Okay, if there are no further questions, let's thank the speaker for a very interesting talk on keyword generation. So thank you very much, Xiao, for coming and speaking in our seminar series.
Thank you.
Thank you.
Thank you for
Thank you.
having me here.
Yeah.
If you have more questions, just feel free to send me an email. I think Edwin knows how to contact me.
Yeah. Okay. Okay, everyone, have a great weekend.
Yeah, thank you. Have a great weekend.
Okay. Okay, thanks again, Xiao.
Thank you. Bye.